Okay, in this particular case, we've identified one-to-one functions as those where the horizontal line applies. Okay, or horizontal line test applies. Now we're going to mathematically determine whether two things are functions, which is going to bring up what was a sore point for some of you on the test. Some of you did not discern the difference in that little open circle that means compose and a time sign. You worked it correctly if it had been a time sign, but that wasn't what the problem was. There were 2 or 3 like that, meaning 2 or 3 questions. Okay. Now, this is saying if both of these things happen, then it'll be a one-to-one function. This says if you take the equation and its inverse and you compose them, substitute G into F, and get an answer of 1x, you do it first, which also was a problem some of you had on the test, was you didn't notice the order of these things. This time you substitute F into G, and if you get 1x again, then this thing is a one-to-one. Now, here's a little caveat. If this one's not 1x, there isn't any point in doing that one. Don't bother. Okay? So here's another way of doing it using the inverse notation that I introduced the other day. In this case, this means take the original equation and the inverse. You substitute this into that if you get x. Here, you take the inverse, substitute the original into it, and if you get 1x, a one-to-one function. These two things basically say the same thing, it's just different notation. Is all that it is. Okay, so let's prove that, or disprove it as the case may be. Okay, we've got this equation, and we got that equation. Allegedly, they are inverses. We need to test them to see. So, the first thing we're going to do is we're going to do G into F. So we're going to substitute this value into that x. Now, when we do that, it simplifies to here. 3 times a third is 1x, and 3 times 2 is 6, -6. And then ultimately, those two are going to cancel, so you get an answer of 1x. So far, things are looking good. We'll see if it continues. Now we're going to take G compose F. Okay, so in this case, we take the G equation and we put 3x plus 6 where the x was. We substitute it in. Here's that tail along -2. We multiply a third times everything in the parentheses, and it simplifies to that. And then that becomes 1x. So in this particular case, both of these come out 1x. Therefore, these two equations are one-to-one. What's the other implication of this? They're one-to-one, so what? Then that means that these two truly are inverses. Okay? Okay, here are 2 more. Same process. Okay? By the way, look at the shape of this one and look at the shape of that one. Okay? Well, let's do F compose G, so we'll put this into that. There's supposed to be a 5 right there. That's supposed to be a 5. Okay, and what happened was I scooted this up and it crowded it out. Fact is, I should fix that. As long as, well, if I move that one, then I gotta move this one. And I'm still okay. Okay, so that simplifies. Okay, the 1 and 1 make 2. Here we got the 5. 5 goes into 5. 5 doesn't go into 2. So basically, that's not going to be X. Because of that, we don't need to go any farther. We know that these two are not inverses, and we know that they are not 1-to-1. Now, look at that one. Here they're doing it the other way, just to show you. And that one isn't going to come out 1x either. Okay, here's 2 more problems. This one and that one. Okay. Here's the work on this one. Substitute G into X. Simplifies more. We don't get 1x. We don't need to do any more. We know they're not 1-to-1. The other one. Yeah. Okay. We replace the x in M with 2x plus 5 over x, which means we got a compound fraction. Okay. We put a common denominator under this 2 by multiplying it by x over x, which lets us then simplify over x, 2x plus 5 minus 2x. So those two cancel out, just leaving this 5. And over here, that 5 comes across. But I wanted to show you how this became that. Okay, so now, in this case, I've still got a compound, so I'm going to flip and multiply that, which is what I did here, flipped and multiplied, and I did get 1x. So now I have to test the other way. Well, here's the other way. And it's even uglier, because it has a really compound one. Okay, we find out my common denominator is x minus 2. So I multiply x minus 2 times every term, like we've done before. Okay, then we cancel wherever we can. These two cancel, leaving me 10. Here I just get 5 times x minus 2. And all of this is, when these two cancel, all of this is over 1. These two cancel, leaving me a 1 down here and a 5 there. So now I distribute that 5, and it does become 1x. So these two indeed are inverses. And my scribbles are even half legible on this one. Anyone not ready? Okay, find the inverse of a function. Now we're actually going to do it. Okay, all we've been doing up to this point is we've been determining if I tell you they're inverses, are they really? Now we're actually going to take an equation and find its inverse. Okay. Okay, here's your procedure. There are 4 steps. You might write these down. Remember, you've got your function notation on the original equation that we're starting with. So we're going to consider these 4 steps now. Okay. Here's the equation. F of x equals this. The first step just said simply replace that with y. The second step said interchange the x's and y's. Remember when we had those sets of coordinate points, we reversed the x's and y's and it gave us the inverse? Well, that's what we're doing here, reversing x and y's, interchanging. So here's the second step. Now, typically the third step, which says isolate y on one side of the equal sign, is the hardest thing in this whole process, because sometimes that can take 3 or 4 steps. Okay. Well, in this case, we're going to take that 2 over and we're going to multiply everything by 2. They decided to multiply everything by 2 on both sides. What they did was this. Okay. So 2x here, they got 2 times 2 is 4, 2 times a half is 1. That's the way they did that. You also could have done that, right? If you got x equals 2 plus 1/2 y, you can take the 2 over and get x plus, or x minus 2 rather. X minus 2 equals 1/2 y. And then multiply everything by 2. And you would get 2x minus 4 equals y, which is what they will get on their next step when they take this 4 over to the other side. So this is one way of doing that. That's the other way of doing it also. Doesn't matter which way you do it. So that's the third step, is to isolate the y. And then the final step is just simply replacing this y with the F inverse notation that we had before. That looks like that. And that's your 4th step. Now, any question about these 4 steps? Let me erase this. And then we can go on. Now, if we graphed this equation, okay, here's the first equation, here's my y-intercept, and my slope goes up 1/2, so up 1 over 2, up 1 over 2 for that first equation. For my y-intercept, or my inverse rather, then -4 is my y-intercept, and the slope is up 2 over 1, up 2 over 1. Now, I told you before these things always reflect across a 45-degree angle through the origin. Okay, and as you see, they do. By the way, that's the x equals y line, or y equals x line. Yes.
So for an inverse, it'll be the same slope, just the numbers are flipped.
Well, they're gonna have reciprocal slopes,
Okay.
but don't try to take a shortcut with that one. Okay, now what they're about to do is they're going to do the Compose test. Okay. Just to prove that what we did is truly 1-to-1. So I'm gonna go through this pretty quickly. Whoops. There, and you see it does equal 1x, it does equal 1x. We're not teaching the compose trick again. Okay. Step 1, replace f of x with y. Step 2, interchange x and y. Step 3, isolate the y. Step 4, in the f f inverse notation. And that's supposed to be a negative right there. Remember, that is not a power. It's just a notation. So supposedly, if we did the compose thing on these two equations, I would come out with 1x both ways. Here we've got a rational one, variable in the denominator. Now, with this, we have an asymptote. We have a no man's land. We have an electric fence. Okay. In this particular case, if x plus 1 equals 0, take that over, x would be equal to -1, so that's the value it can't be in the denominator. So what that means then is I've got an asymptote, a boundary line that can't be crossed right there. Notice how this thing approaches here. And this one would approach there, but it'll never touch it. Okay, now, this is the original equation. Here's my 45-degree line for later, or after I put up the inverse. So let me erase this. Now, let's go ahead and find the inverse of this thing. So, in this case, here, we just replace the f of x with y. Now, we're going to interchange the two letters. And I started step 3 here. Okay. Since I had a y plus 1 in the denominator, I multiplied both sides. That's supposed to be a plus sign. That's supposed to be a plus sign. Kind of, maybe, whatever. Okay, now that gives me this and that, because these two cancel. Okay, and I'm still not got y isolated. Well, I distribute this x and I still don't have y isolated. But you know what? I've got a y in this term and I got a y in that term. So how about I take this term over to the other side? When I do that, then I've got this. This x equals that 3y minus this xy that I moved over. Now I can factor that y out of those two, like that. I don't want this with that y, so I divide both sides by it. Because I want that y by itself. Like I said, step 3 can be a pain sometimes. Okay? Okay, that simplifies. When I divide both sides, these two cancel, and I get x over 3 minus x equals y. So this, when I put in the notation, should be the inverse. And I bet someone on the test forgets this last step whenever it comes. Okay. Now, we could test these by composition to see if they are truly inverses and 1-to-1, and we didn't make some mistake. Now, let's see what this thing looks like. Let's graph it. Okay, here is the inverse, here is the original. The blue is the original. I've already drawn in my asymptote, my reflection line. If I do XY on this to graph it, it would look like that. Okay. These two are reflections of each other across that, and these two are reflections across that. Now, notice this one and this one, these inverses, the asymptote swaps on that. Now the inverse, the asymptote is over here. Okay. For the inverse. Yes.
So that F-1 is basically just like showing that it's like on the other side.
Right here. Based on that.
Oh, okay. I was talking about like the on the left side, like the F to the -1. Yeah.
That is not a power.
Oh.
That is a notation that means this is the inverse of that.
So it's like on the other side.
Well, this is that orange, and that is the blue when you graph it. I don't know if I've answered your
No, you
question.
did. That's what I was asking.
Okay. Any other questions on this one? Okay. Okay, well, here's just the composition test. And it works. Okay. And here's the other direction. Which is a pain. Okay, I'll admit it. But the question didn't ask you to do it. It's whether you want to gamble what you got's right. Okay, what about this one? Now, on this one, that is a parabola right here, shifted up 3. That equation in its entirety. Okay. This disclaimer is throwing away that half of the parabola. Now, why might we want to do that? If I have the whole parabola there, what visual test will not let it be 1-to-1?
Horizontal line.
The horizontal line test won't. But by excluding all of this on this side of the axis, then the horizontal line test works. So I have a chance of it being 1-to-1. Okay? A chance, not a guarantee. But if that's there, I've got a guarantee it's not. So anyway, that's why they put that that disclaimer or that restriction on it? Well, here we go. We replaced f of x with y. Now, watch what happens to the disclaimer when we interchange the x and the y. The disclaimer also interchanges. That's important. Make yourself a little think note on that, because that's big. Because this thing right here is going to say that our answer can only be up here and not this part down here when we graph the thing. Well, here's step 3 coming in. Step 3 is a little bit, oh, that's a 2 right there. Let me. Okay. Get rid of that square. We have to take the square root of both sides plus or minus. Square root of y squared is y. Here we got that. Okay. It simplifies, and then finally we replace the y with this. If we graph this business, then square root of x goes up like this, normally starting at 0. But this says we're going to shift it 3 places to the right. Remember, anytime it's contained inside a parentheses, under a radical, inside an absolute value, it goes opposite direction or opposite of sign. So 1, 2, 3 to the right. So we're going to start here with graphing that. And when we do it, it'll look like that. And here is the restrictions we can't have, because if we had that, we couldn't pass the function vertical line test. So that's why we had these disclaimers, is so we could pass the 2 line tests. And as you see, this thing and that thing do reflect. Questions on this one before I go on? Okay. All they're going to do right now is they're going to test it. Okay. Goes that way. Now they're doing it the opposite way. And it works out too. So here's another one. Given this equation, we got a restriction again. Why? Because this thing is a parabola. And we're going to throw away half of it. Okay? This time we are keeping the left side and throwing away the right side. Okay? Well, here we replace the n of x. We interchange x and y. We solve for y equals. So here I put in my f inverse, that's -1 right there, supposed to be. Okay, equals this thing. So that is my equation for the inverse then. Now, in this case, graph paper. The first equation, up 1, it's going to go like that because we threw away this half. Second equation is going to, in this case, well, if this is 0, 1, then 1, 0. If this is -1, 1, then this is, negative. If this is -1, then this is 1, -1. Okay. If this is 2, 4, I'm just gonna call it, then I would have 4, 2, and this is gonna be going out like that. That means what?
Why would the inverse not be going in the opposite direction?
Everything is a reflection, interchanging the X and Y values.
Oh,
Okay, that makes graphing it easy. You don't have to do an XY table. Just take this, find some points, reverse the letters or reverse the X's and Y's and graph it.
okay.
If you want to be fast and lazy. If you want to be accurate, then do an XY table. Okay, here's another one. This time, we're still talking about a graph to start with. Graph paper. We're talking about a graph that's going to look like this way, start and go up that way. That's what that original equation is going to look like. Okay. Now, we interchange. Okay. And we simplify. And ultimately, this becomes our inverse. The 4-step method. Okay. Well, what's this one going to look like? If this is the point, -2, 0, then here I would have the point 0, -2 right there. Ultimately, and here is the point 1, -1. So I would have negative, if this is 1, -1, or a -1, 1, -1, 1, then I would have 1, -1. And this one is gonna go up like that, and they are gonna eventually cross at the same place if you do it right. Okay. This we've seen before, different variations of it. Okay, graph the inverse, we'll figure out what these 4 points are. Reverse the letters on them. Graph those, and there you got it. I really anticipate a problem like this one being on the final. And perhaps mine. Okay. Now we're leading into exponential functions. Now, previously, we've had things like this where the base was a variable and a number was a power. Okay. Now the difference is the base is going to be a number and the power is going to be the variable. So these are exponential functions, ones that would look like this. Okay. So that's the difference in just basic exponents and exponential. Now, look in your folder packet from page 17 to page 20. Page 17 to 20 is a whole bunch of stuff with both exponential and logarithmic, which is where we're headed. Okay. Some of those pages are sample problems that you work. Okay, let's go on. Now, this is saying that B has to be a positive number. That's what that says. And it also says B can't be 1. Okay, so if it's a positive number, it's either got to be a fraction or it's got to be a counting number, just not 1. Why? Because 1 to any power is still itself, is still 1. And we'll talk about that. Okay, 3 to the x. Well, if we work this out, by the way, I did y equals x cubed for comparison. Okay, here's the graph of y equal x cubed. We've done that one many times before. Now, here is 3 to the x. 3 to the x is what we call an exponential curve, and it's going to look a whole lot just like starting here and that way. Okay, well, 3, if you let x be 0, you get a 1. Okay, so you get the point 0, 1 right there. Okay, if you let x be 1, then you get 3. So 1, 3 up here. It's a little steeper than that one. If x is 2, then you get 9. So 2 and up about there. And anyway, this curve, and here's some negative exponents. What do you do with negative exponents? You flip it. You flip the base. What?
Wouldn't 3 to 0 be 0?
Nope.
Or would it just be?
Anything to the 0 power is 1. And that's one of the statements on those sheets that I gave you as well. Okay. So anyway, these are approaching infinity, are infinitely close, but never attaining. Then we 1 over 81 and 1 over 243 and whatever 2 to the 3 to the 5th and 6th and 7th. Anyway, here's what the curve looks like. Here's that part down here. X is negative values. And we are getting closer and closer and closer to the x-axis, but we will never quite attain it. Okay, unless there's an up or down shift. And there's not in this problem. Up here, this thing's just going to keep going. It's still going that way, but it's going steeper upwards. Now, let's continue. 2 to the negative x. Uh-oh. Well, here's the graph of 2 to the x. Let me pull this up until I get the graph paper. There we go. Here's the graph of 2 to the x. If x is 0, okay, if x is 0, then y is 1. If x is 2, y is 4. If x is 3, y is 9. Somewhere up here. This isn't perfectly accurate, but you get the idea. Now, what does this negative power do? This negative power could always also be this way. Remember, when you have a negative exponent, you can flip the base. So this means the same thing as 1/2 to the x. Now, let's go way back to when I first started talking about flips across the y-axis and across the x-axis. Okay. What could you do to the x values to cause it to flip over the other side of the y-axis? Symmetry. Replace x with negative x, right? If you replace x with negative x, it flips it across the x-axis. So if this is 2 to the x, then 2 to the negative x better be a reflection of this one. And by the way, those are supposed to line up there at 1, at 0, 1. This one and that one should be symmetric with respect to the y-axis. Okay. You can see here, we're getting closer and closer and closer with these values right there. Okay. Well, now they actually draw the 2 exact curves. Okay, what about this one? That and this can be renamed as 5 to the negative x. So if you're working smarter, not harder for Carter, you can graph this one, which is pretty easy to graph. Okay. And then just mirror image it across the y-axis instead of figuring them both out. Here's approximately what that one looks like. Okay, we got the point 0, 1. Then if x is 2, or x is, and then we got the point 1, 5. Then down on this side, if x is negative 1, I've got 1/5, then 1 25th, then 1 1/25th, then 1 1/65th, and our 625th, and so on. And that's as far as I got them memorized. But anyway, if that's this graph, well, what do we have to do? Well, just mirror image it to get the graph of the other one. And as you see, when you do an XY table, they do reverse across the axis. And this talks about the reflection. We got a more complicated equation now. Basically, we're going to take 2 to the x, which we had on that last one, right? And we're going to shift it one place to the left. Because technically, there is a parentheses around that. So that means we're going to have a one shift to the left, opposite sign, of the 2 to the x graph. Then we're going to flip it upside down. That's what that minus there is going to do. Then we're going to move it up 1. You follow me on these transformations? Anyone not? Stop me right now if you don't. I'm getting a lot of real blank stares. Okay. Graph table. 2 to the x goes to the point 0, 1. If x is 0, y is 1. For 2 to the x, if x is 1, y is 2, 2 to the first power here. If x is 2, then 2 to the second power is 4. And this thing goes up like that and starts going down like that. Okay, that's just the 2 to the x by itself. Okay, I have a modifier with the x. Okay, that means that I'm going to have a shift in every one of these x values, left or right, and in this case, left. because it's always opposite sign. So that means just that, okay, just this part is gonna take this graph compared to 2 to the x, y equals, compared to this, that is going to shift everything here one spot this way. And this thing is gonna go like that. That's just that part of it right there. Are you with me so far? Okay. Now that negative. That negative in front of the x is gonna flip it upside down. Make it go downhill instead of uphill. Okay? So this point is gonna be here. This point is gonna be here. This point is gonna be here. This one here. This one here. And this one here. And now this thing's going like that. And are you still okay? Now this one is going to raise it up, raise this one up one place. So this point comes up to here. This point comes up to there. This one about here. Let's see, about there. This one here. This one here. This one here. This one here. And this thing now is going to look like this black, the ultimate graph. Okay, that's what these transformations tell you. Okay, it might have been easier to understand if they had written of x equals -2 to the x plus 1 plus 1, if they'd written it out that way, which is the way you're used to seeing it more. Okay? It might have been easier if that one had been on the other end. And you can do that if you wish. I mean, that's perfectly okay. So anyway, that's what you got. Now, they did an XY table. Actually, so did I, but I just rattled off the numbers. Okay, this is that whole thing when you replace that x with 0. Okay, 2 to the first is 2, makes it -2, and 1 minus 2 is -1. That's how they got all of these. Like I say, it's kind of a pain. Anyway, they got these, so let's see, 0, -1. Let's see how close I was. 0, -1. 1, -3. 1, -3. 2, -7. Out here's 2, -7. So I was pretty close. Okay, pretty close. And whoops. Come on. There's the 2 to the x, and here is the equivalent of my black line. Okay. Did that help? I hope. You sure? Do I need to try again?
No.
Okay.
So the black line is what we're problem.
Yes.
Yeah, the black line is the answer. These are just how you get there from transformations.
Red, orange, and blue, which is basically what you're
Yeah.
watching.
Uh-huh. Or you could just do this to start with and graph it in one shot. Okay. But that depends on you knowing what this one looks like to start with. Okay, here they're just kind of explaining what happened to it in the equation. Okay, this business right here shifts left or right, opposite of sign. That shifts up or down. This multiplies it, makes it steeper, makes it shallower. Or if it's a negative, then it flips it. And that's what that stuff is saying. Let's see, I've got a little more I can add to this. Okay, here's the same problem. You notice this time they put the 1 in the back. Okay. This same problem I had before. And these are just the things that I did. I shifted left. I reflected. And then I moved it up 1. I moved the reflection up. And a summary of the steps. And there's the graphs again, the terminal graphs. Okay, this time we're doing 2 to the negative x power or to the 1/2 to the x, because those two things are interchangeable. This one I think is easier to calculate with. Okay, so anyway, here are the basic 2 to the x. Here are the 1/2 or 2 to the negative x. You notice these are just reversed. Okay, and there are the 2 graphs. Because basically all that negative does, if you got this one, that negative is going to flip it across the y-axis. Okay, what about these 2? Remember, this is the same as 3 to the negative x. Okay, here's the 3 to the x graph, and there's my XY table for it. Okay, this keeps getting closer and closer. Here's that point 0, 1 again, and here's 1, 3. And the next one would be 2, 9, and so on. Okay, and then so -2 is 1/9. Well, here's that one. Just simply reflected across. But there's the XY tables if you want to look at them. Here's where we want this one. This is the same thing as that. Well, the 3 to the x will always start here at 0, 1 again. When x is 0, we get 1 for y. If x is 1, we get 3. If x is 3, we get 9, and so forth. So here is that basic one. This one is a reflection of that one. So it's this one in green. Here's the XY table if you wanted to do it. Okay. I'm trying to teach you to work smarter, not harder, but that means you got to kind of learn what to look for in these. Okay. Well, here's just a summary on that. Some language. A graph going down this way is called decay. One going this way is called growth. Okay, kind of obvious if that were in a business chart. Okay. The domain and range domain, of course, is infinity to infinity. And then the range starts with 0, non-inclusive because this never quite touches it, on up higher. Okay, here's one similar to what we did before. Here's the 2 to the x. We've shifted it 2 places to the left. Now we're going to move it down once. Okay, E. E is a number used in growth rates. It's very similar to pi in that it is an irrational number that never repeats, never terminates, but keeps going infinitely. Okay? Now, what they're saying, this is how they calculated the value of E. That's not something you really need to be worried about, okay? Except a variation of that's going to show up in an interest formula in a little bit. So here, this you do need to know. You need to know at least 2.718 minimum memorized. And that is approximate because that's a rounded off value. So in other words, it's almost 3. So if I had a graph of e to the x, it's going to be very similar to the 3 to the x graph. Okay, just a little less steep, but not much. Calculator. If you want to put an e in your calculator, the Castios that I have you use in case you want to get it out. By the way, from this point forward, you need to have it with you every class. Okay, from this point forward. First, the alpha key. Then down here is this little E right here. Then you hit it, and that'll put an E in your calculator. Okay. Now, if you want to E to some power, first thing you do is you put the E in, and then you hit the unknown power button. If you want it squared, you could use that one. But if you want to put anything else, you use the unknown power button, and then you type in this case, a 2. All right. And then finally, you can hit the equal button, and you may or may not have to hit the standard decimal button to get an answer. Okay. So E squared is about this. Or in other words, almost 3 times almost 3. Any question on how to find E? Okay. There's E rounded to, the previous problem. That answer we got here. They just simply say round to 4 decimal places. 1, 2, 3, 4. This 5 impacts that 4th one, tells it to go up. So in this case, your answer would be with the 1 up. I mean, that's 4th grade stuff right there. E to the -3 power. Well, you put it in your calculator the same way, except when you put in that power, you hit the negative button, then the 3 instead of the 2. Okay, what am I talking about? Let's go back to this one. Okay, I had the box here. Instead of punching in a 2 this time, I would hit -3 equals. Okay. And that's what the value would be of that. Oh, we're getting ugly now. Okay, I think I need to get out my calculator. which means I've got to get out of that and put it up there. So alpha E and power, what are we doing? Square root of 7, square root of 7 equals, okay. That's the nice thing about these Casios. What you see is what you got. You put it in just like you would if you were writing it. Okay. Well, e to the pi. There ought to be some kind of a joke I could make about that that would be a groaner, but I can't think of one at the moment.
Hope it tastes good.
Yeah. Okay, so there I have my e to the power of, and now to put pi in there, I've got to hit the shift key. See, this first one is pi, the second one is e. The first one you have to hit the shift key to get. So shift, and then that key, and equals. Graph the function. Okay. Well, honestly, the way I would do this one, if they just said graph this function, I would do the e to the x, and then I would shift it. This is the e to the x. See here, it still goes through the point 0, 1, because even e to the 0 power is still 1. And then on up this way, basically the x key, I mean curve, very similar. And then I would do everything over one place and try to fool Mr. Carter that I know what I'm doing, instead of doing all of this. Now, could you do that in your calculator? You betcha. Okay, let's pick that -2. Alpha E power -2 plus 1. -2, and I've got to do the plus 1. Okay, now this may force me to put in parentheses around that. Okay, this may force me to put parentheses around that, and I think I've got an extra term in here, an extra space that may mess me up. Nope, I didn't. Okay, now I can hit my equal sign. Okay. They're saying that this, for graphing purposes, rounds up to 4/10, or a little less than half. Okay. And so at x equals -2, we're a little less than half. So anyway, that's how you use your calculator. Okay. Okay, this one just asks us to explain. This one, so how is this, if we start with this, how does that end up? Okay, this is kind of like the ones before. Well, here is the e to the x. Right here. I got it graphed. Here's that point 0, 1. Because these are 2's. Okay? Now, this part is going to shift me one place to the right. This point became here, this point became there, this point became there, this point became there, and so on. This negative is going to flip me. Okay? So this point becomes here. This one becomes here. This one becomes here, and so on. Okay, so what are we doing here? What changes do we do? The x minus 1 shifts one space to the right, and you're going to have to write out explanations like this. Okay, that's your expectation. Then the negative flips it across the x-axis. And I need to get rid of my dots. It'll look real cute in the video, won't it? Okay, now interest. And I do have to get this covered tonight. Okay. There are three formulas for interest. You are expected to know all three by memory. Now, this is simple interest, typically based on time of 1 year. Okay. Time is automatically 1 year unless they tell you something different. Now, interest is the amount they pay you for using their money, or you pay them for you using their money. The P is the original amount you borrowed or loaned. The R is the interest rate converted to a decimal. And the time in year proportions per year. For example, 6 months would have to be 0.5 or 1/2. Okay, 9 months would have to be 3/4 of a year. Now, this one, if they say it's the interest is compounded, that means you build on interest. Okay, this one you just get a simple interest out. The other one, it takes the interest you earn, reinvests it, and it builds faster. Okay, now if they say it compounds semi-annually, or quarterly, or monthly, which is 1/12 of a year. Okay, semi-annually being a half. Okay, or something like some interval like that, then this is the formula you have to use. Now, what does this mean? This means the total accrued amount with interest on interest is equal to the amount you borrowed times 1 plus the rate over the number of times that it's calculated times the number of years that you got it in there. Okay, and that's what this is. And you can do this in that calculator. Okay, and I'll show you that in a moment. Now, if they say it is infinite interest, then that's this bottom one. The accrued amount is the amount you borrowed times e to the rate times the time, hour-wise. Okay, every year in the 20 years that I've taught for WSU, there has been a problem on the final that said so-and-so had an account, a loan, and the interest was done. They can either say simple, they can say quarterly, monthly, semi-annually, whatever, or they can say continuously. Continuously and infinitely mean the same thing. And you are expected to know which formula to use. Now, if it said continuously, what if they said yearly? What if they said yearly? Then you got to use the middle.
I'll leave the middle one.
Because you could have multiple years. And you would accrue interest on that years and so on. Now, a mistake that some students have made is they put in 365 in. The N is 365 for days in a year. Okay, that would be considered daily interest. Okay, daily compounding would be 365 times a year. Believe it or not, the difference in 365 times a year and continuously for 1 year is a measurable amount. Even though it might be a decimal amount, pennies. And that'll make a difference in you getting a 4-1. Time to use those three is big. Okay, here's an example. This one's compounded annually. Okay. Compounded annually, they want you to do it for all three options, okay? Compounded annually here, we got this, we're putting it in here. And why is this only 7? Because N is 1 for a year, once a year. Okay? Daily, you have to put 365, but it said annually. So then that would be a 1. And then for 7 years at the interest rate of 0.05, and this 1 plus is what actually adds within this equation to make the accrued amount grow. Okay, now you put all this in your calculator. Okay, let's do that. In this case, I'm basically going to put this string of values. So I'm going to type in 1500 or 15,000 rather. Parentheses 1 plus fraction. The rate 0.025. Okay, 0.025. Use the arrow key to get down to the basement. Over 1 in this case. Because it's 1, I wouldn't have really had to have done that. Now I'm going to get out of that fraction. I'm going to put a parentheses. And I'm going to put a power of. Now, if I wanted to put 1 times 7, I could, but it seems kind of unnecessary. Equals.
Is that a different equal sign like the, or is it just?
I just did this one.
I don't know, like I know that's right. I'm just curious because.
Oh, this is approximately, because this is a rounded value.
But there's no, you can't do that on a calculator, can you?
You got a single squiggle on a calculator.
Is that what that's-
No, when you write it on you see what my calculator's got.
Okay.
You've got to know that it's a rounded value.
Never mind.
Okay.
I get it.
Did that answer your
Yes.
question? Okay, so anyway, you see how you do this thing? Okay. Let's go to the next one. Now we're going to compound quarterly. Okay. I don't need to change everything in here. Okay, because the 15,000 is the same. The 1 plus, that's the same, but that has to be a 4 now. Because I'm doing it 4 times a year. So I back up and keep backing up until I get there. I delete that, put in a 4. Come back out here and hit my power key again. Whoops. I've got to, let me completely, there we go. So now I've got 4 times a year times 7 years. Now I can put in 28 or I can put in 4 times 7, but I better put it in a parentheses if I do. So I'm going to put in 28 and equals. Okay. Did I get more?
Yeah.
How much did I have this time compared to last time?
17,858.96.
I got about roughly $20 more by doing it quarterly instead of now continuously. Now we're going to use the P equals E to the RT formula. A equals P times E to the RT. Okay, just like this, P times E to the RT. So I'm going to clear this out and just start all over this time. 1,500 or 1,000, okay, times, that's the P. Now I'm going to put in the E to the power of, and this time I've got 0.025 times 7. Close up that parentheses, and now I can hit my equal sign. So as you see, I even made more money, an extra $10 compared to quarterly. So interest calculations make a difference. Okay. And with that, we're going to have to stop.